Hello, everybody. In this video, we're going to go over basically how to deal with type 1 improper integrals. Unless anybody else has any other questions, feel free to drop them in the chat or drop them in Skool. But otherwise, we'll just continue with where we left off yesterday. So first, let's just actually do a brief summary of where we left off. So we talked about this idea of improper integrals. And basically, the thing that makes it improper is that there's an infinity somewhere, either in the input or the output. If the infinity shows up in the input, like these two things, for example, see the negative infinity on the bounds, that would be a type 1 improper integral. And that's the simpler type. That's what we'll talk about today. Type 2 is if it shows up on the output. We'll deal with that later. But for now, we're going to talk about type 1 improper integrals. And before we do that, just as a refresher, like how is it possible that when we talked about the words converge and diverge, converge means that even though there's an infinite width, basically, there's an infinity in the input, the integral still equals a finite number. That's what it means to converge. Whereas if it does not, there are some functions where it does not, most functions actually, that would be an example of diverge, basically where you have an infinite area, which is what you might expect. The only way, remember, is that we can have, for us to have a convergent improper integral, is to have the bounds is to have a function that decreases fast enough. If it decreases fast enough, it's true, we'll always be adding area, but we'll be adding such little area that it's never enough to flip the higher decimal places. So that's how we can keep having those numbers get bigger forever, but still never break through the ceiling of 1. And that's why we can say that the area is actually counterintuitively has an upper limit of a finite number. It doesn't just grow forever like you might expect. So there you go. Hopefully that idea makes sense. Now let's dive into how to actually do this. So here, and I think I gave the process last time, actually, if I remember correctly, yesterday. Did I say? Yeah, I think I described the process. So this is actually a good one to start with. Let's start here. Basically, the process, if you wanted to break it into a couple steps, one is step one. So step one is basically write the limit expression as we have done here, right? Step two is solve the integral normally. You'll get a function of b, not a number, right? Normally, when you solve a definite integral, you just get a number, and that number represents the area under the curve. Here, because b is a variable, you won't get an exact number. You'll get a function of b. You'll get an expression basically that tells you the area under the curve for any specific b value, like the upper bound, for example. And then step two is solve the resulting limit expression. So step three, solve the limit expression, right? After we solve, again, you'll see how this plays out, but after we solve this integral, we'll get like some function with b in it, and then you'll still have the limit on the outside. You just take the limit as b goes to infinity of that function, whatever it is. And then you'll either get a number, you'll either get infinity, which means your answer is diverge. You'll have an infinite area. It doesn't really make sense to say that there's a finite area. That's possible. Or what can happen when it converges is that it actually equals a finite number. So counterintuitively, in that case, we would actually have a finite area, even though we have an infinite width. So that's kind of the first three steps. We've already done step one. This is always step one, what we've done below. Now let's actually just solve the integral. So think about it. How do we solve this integral? The antiderivative is natural log of x. We evaluate it between 1 and b. And again, I'm just going to hold the natural or the limit expression on the outside. And then basically we evaluate between the bounds. So we have limit of natural log of b minus natural log of 1. What's natural log of 1? 0. So we don't have to worry about that. That's 0. So long story short, we get, or whoops, I'll just rewrite it. We get natural log of b. And we need to take the limit as b goes to infinity. Whatever this is, that'll tell us our answer for the integral. So here, think about it. As b goes to infinity, what does the natural log of b do? The only way to do this is to really get familiar with what the natural log graph looks like. That's the most important part. So here, if I show this, for example, let me actually just graph natural log of x. You need to know that this is what the natural log graph looks like. So you might think that as we go to the right forever, that's what the limit as b goes to infinity or x goes to infinity represents. You might think it seems kind of like we're leveling off to 4, but we're actually not. We're actually not. If I zoom out enough, you see this, like once I go out to here, once I go way far to the right, we've surpassed 4. And this is true of everything. Like if you shrink the input enough, if we shrink the input enough, and again, you have to shrink the input by a massive amount to be clear. So here you can see I'm saying like 1 square is now worth 100,000 units, but you can see if I do that, I can get up to 11, which seems like very small. So the natural log, the behavior of it, it actually diverges as you go to the right forever. You go up forever. You just go up forever extremely slowly, but there is no upper limit actually. If I keep increasing or if I keep decreasing the x-axis, you can see now I'm not 11, I'm above 20 now. You can hit any number you want. It's just going to take a long time, but you will get there. There's not like a hard upper limit. Compare that to the function that looks like this: one over x plus 3. This, or 3 plus 1 over x. This has a hard upper limit. If I go back to the beginning, this, or actually let me say minus. That'll probably look better. Yeah. So let's say that, and let's actually only talk about it when x is greater than 0 as well. So this one does have a hard upper limit of 3. So this has a horizontal asymptote, right? When you look at it right now, or if I zoom in a bit, when you look at it like this, it might look like both of them have a horizontal asymptote of 3. The blue one does, but the red one does not. Like the blue one, if I keep going to the right, the blue one, like you can see what's happening. The red one slowly but surely goes up and up and up as I go to the right. The blue one does not. The blue one gets stuck. It's not actually at 3 right now. It's actually at like 2.999. It's just that the calculator can't really represent the difference because it's so small. That's what's actually happening there. So, in other words, you got to be careful with these. So, just like when you're looking at natural log, even though it kind of looks like it levels off, it doesn't. It actually never levels off. It just goes up extremely. It goes up forever. You can make it as high as you want. You might just have to plug in a gigantic input to do it. So it goes up. It goes up forever. It just goes up very slowly forever. That's all. So there you go. Hopefully that idea makes sense. So that's that. Now what should I say? I guess how. So yeah. So I'll just say that. Now let me say. Or actually, let me mention this as well. Square root of x is kind of like this too. So like square root of x, if you ever like, because when you solve the expressions that you might end up with square root of x sometimes, that has a similar behavior to the log. It goes up forever. It just goes up very slowly. It goes up faster than the logarithm, but it technically goes up. That's all that really matters. So long story short, you need to understand that behavior of the functions you're dealing with at this point. So basically the answer here is infinity. What that means is diverge. It means that this function natural, or sorry, 1 over x does not shrink fast enough. That's essentially what we just found. It does not shrink fast enough. So as we go to the right forever, right? Let me actually grab the same animation we were using last time. Just a second. Let me grab that integral. Yeah, this is what I want. And if you're in the Skool community, you can always you can check the Mila Note link. It's in the classroom tab under like daily live notes, I think it should say. But you can check this and you can see what we talked about on this date, 128. But if you come back here, if I actually talk about what I'm dealing with here, that's the function 1 over x. I'm going from 1, and I'm going to widen that just so it's more obvious. And then basically I'm just going to keep dragging b to the right. And basically what's happening is that this value, as I keep 10xing the input for b, this number just keeps steadily going up. It's going up very slowly, but it is going up forever, right? It doesn't seem to be slowing down. And here, that's where we break the calculator. So instead of having an actual number here, I'm just going to type in infinity. And you can see that the area under the curve is undefined, meaning there's an infinite area. So diverge. That's what we just got by hand. So we got the answer by hand. So that's good. So hopefully that makes sense. That's an example where it diverges, and you can see the process, right? You have the first step is you just, wherever you see the infinity, make it limit as b goes to infinity of that, which we did. Then you just solve the integral normally, which we did. And then finally, after we solve the integral, we're going to get a function of b. And then you just take the limit of that. That's the last step. Solve the limit expression. Limit as b goes to infinity of natural log of b. In this case, that's infinity, so the answer is diverge. If it was a finite answer, the answer would be converge, and it would converge to whatever number we got. Converge just means the area is finite, the limit exists, basically. Infinity means it doesn't, or diverge means it doesn't. So hopefully that makes sense. Let's do another one. So let's take a look at this one. And again, it's the same 3 steps, really. Well, let me change the function. So let's say instead of 1 over x, let's do 1 over x squared. And then it's the same function, basically. So how do we do this? Again, step 1, write the limit expression. Instead of leaving the infinity there, we'll do limit as b goes to infinity of integral from 1 to b, 1 over x squared dx. So that's step 1, done. The hardest part is still solving the integral, by the way. Once, like, that's the hard part. The first and the last step should be pretty easy if you solve the integral properly. So here, how do we solve this? Remember, think about this like x to the negative 2. So if we do the anti-power rule, add 1, x to the negative 1, and then divide by negative 1, negative 1 times x to the negative 1. So in other words, negative 1 over x would be the antiderivative evaluated between 1 and b. I'm just going to keep the limit expression until the end. So keep the limit expression, and then what's this going to be? Negative 1 over b minus negative 1 over 1, or plus 1, in other words. So what do we get? We get positive 1 here, minus 1 over b. I just swapped the order. We get this. What is the limit as b goes to infinity of this expression? Think about it. If b is like 10 million, what is 1 minus 1 over 10 million? Well, 1 over 10 million is like 0.0000. It's like 6 zeros followed by 1. A very small number, in other words. So basically 1. It does not infinity. So this one converges, and it converges to 1. That's what we're seeing here. That's what we found by hand. Now let's try it out. And we tested this yesterday, actually, so we already kind of know it works if you remember what we did yesterday. But here, if I wind down here, basically what we're saying is as I drag b to the right, this number should get really, really close to 1, that area under the curve. Oh, sorry, I didn't change the function yet. My bad. Let me change this one. I didn't change it on Desmos yet. So there we go. So as I go here, again, when I go to b equals 10, I get 0.9. When I go to 100, 0.99. When I go to 1,099, it's obviously getting really close to 1. That's why we got 1 as the answer. The limit is 1. Like as b goes to infinity, the area under the curve, it actually goes to a finite number of 1. This is what it looks like for an improper integral to converge. The height is shrinking fast enough now because, right, 1 over x squared, that shrinks a lot faster than just 1 over x. Apparently 1 over x wasn't fast enough. This one is. So this shrinks fast enough for the, like, basically the thing that's happening is it's kind of like the 0.999. We're always growing. The area is always growing, as you can see, but it's never grow like the chunk of area that we add, because the height shrinks so fast. The chunk of area that we add is never enough to flip the decimal places of the higher bits. So it's like we're just adding a 9 on the end repeatedly, which is getting bigger for the area, but it's never getting bigger by enough to flip the higher decimal places to get it to equal 1. So that's what it looks like to converge. When it shrinks fast enough, that behavior happens. So that's good. So we've done that one. That one makes sense. Let's do maybe 1 or 2 more. So here, and again, you can see it's the same 3 steps to solve this improper integral. The type 1s aren't that bad. Again, the hardest part of it is actually solving the integral, in my opinion. So here I'm going to say, let's do negative infinity to, like, let's say negative 1 here. So here, the thing that's different about this is now the lower bound is infinity. So how do we handle that situation? It's essentially the same thing, to be honest. So you could say the limit as what I'll say a is approaching negative infinity rather than positive infinity. And again, the reason I said a instead of b, usually when we're writing integrals, think about it, we usually do a as the lower bound, b as the upper bound. So it's like a good convention with improper integrals to write like a, like if you need to replace like here we're replacing the lower one, so I called it a. Whereas in the previous problem, we were replacing the upper one, so I called it b. That's a common convention. You don't have to do that, by the way. You could call it whatever you want. You could call it r, you could call it q, t. You could literally like call this variable whatever you want. It's just got to be a limiting variable. Whatever you replace it with, like whatever the limit is here, needs to be replaced in that spot in the equation. That's all that has to happen. So here I'll just replace that with a, and then we get 1 over x squared dx. Let's solve this. Again, we already kind of know what the antiderivative of this is from the last one. So negative 1 over x. Again, we're just doing the same 3 steps, right? So here, step 1, write it in this limit expression. Step 2, solve the antiderivative. And then if we solve it, think about what's going to happen now. Well, -1 over -1, that's +1, minus, that'll be +1 over a. And then the limit as a approaches -infinity. As a approaches -infinity, this thing approaches 0 again, so the answer is still 1. And doesn't that kind of make sense? Because what we really just found here, we really kind of did the opposite process here. So this is -10,000 on the lower bound. Basically, we're saying b is equal to -1, right? And then we're saying a is actually shrinking to the left, right? So if we're starting at like -1, -1, -10, oops, -10, -100, it's like we're doing the exact same process on this function. We're just literally going to the left. So doesn't it make sense that like this is the symmetrical version of what we just did? So you'd expect this to also approach 1, which we see happening. So both bounds, like either b goes to infinity or a goes to -infinity. That's essentially the options right there. And then yeah, you can basically, as long as you know how to take the integral of the thing on the inside, and as long as you know how to solve the limit expression either or afterwards, these are basically limits at infinity. These aren't that bad in my opinion. They're pretty straightforward, I would say. And if you want to check your work on Desmos, like I said, I have this animation here. Did I? Yeah, I left the link. I'll also pop it on the bottom. If you're in Skool and you just go to the resources, you just go to the classroom tab and just look for daily live resources. This will be the first link. This is the Mila note link. That's the software I use for the notes. You'll be able to find this one and just select that. But that's basically how you do that. And then, if you want to calculate the exact answer, you can just say -infinity. There you go. Desmos is smart enough to calculate the exact answer, even though we never get there. It's really calculating the limit at that point. So there you go. Hopefully that makes sense. That's our introduction to type 1 improper integrals. Like I said, it's as long as your fundamentals for integrals are solid, I don't see the type 1s as that difficult. Type 2s are more difficult, and we will talk about those. Before I go, actually, let me actually come up with. Let me do another one real quick. Actually, I was gonna close out there, but let's actually do another one because this is actually worth talking about. I think. What if we're doing something like this: -infinity to +infinity? What if we have it on both? Let's say our integral is 1 over e to the x dx. This is a little bit more complicated. Basically, step 1 gets a little more complicated because again, we can't just replace both of these, right? So, because like, I'll just say that you can't really just replace both of these. What you need to do is you need to split it at a finite value in the middle, right? And if I just graph 1 over e to the x, let me actually do that again. So if I probably shouldn't have closed out that animation. Just a second. If I say 1 over e to the x, so here, actually, let me say e to the 2x, or let me see. Let me think of it. You can come up with other examples. This is actually a bad example because this one will diverge. Let me actually come up with. Let me see if I can come up with a better example here. Let me try this. E to the negative or x squared over x. There you go. Something like, and then let me scale this up so it's easier to see. So here, you could do this. This is like a bell curve, essentially what I'm looking at now. But this is I'll just leave it as an x there, so it's like manageable to integrate. So let's tweak this a little bit. Let's say let's say this. Or sorry, I dropped my pen. There we go. So looking at this, it'll be x over e to the x squared, and then how would we do this? So the first thing to check is that basically that we have and again, if you look at this, you can probably tell already, right? You can probably already guess what's going to happen here. It seems like the answer is 0 because it seems like it's kind of like the inverse of it. It cancels each other out, and I will say that is right. But here we can prove that numerically. Basically, you need to make sure there's no vertical asymptote anywhere in the middle, right? So we're fine there. And also, this is defined everywhere, right? There's no holes or anything. Like at x equals 0, the denominator is not 0. It's actually 1, right? So that's fine. We don't have any division by 0 problem. So we can just we can basically just split it in the middle using one of our integral properties. Remember that integral property that lets you just basically pick a point in the middle and split it? So here I'll pick 0. You don't have to pick 0. You can pick anything. But I'll say e over x or x over e to the x squared dx plus the integral from 0 to infinity, and then same thing. And then at this, so that's, you kind of need a step before that. It gets tougher to split, but now it's straightforward because you can treat it as two separate ones, right? This one will be the limit as a goes to negative infinity, right? And then this one will be the limit, right? You just look at it as two different versions, like the two that we did independently. You can just split this one problem into like kind of both two of those limits at the same time. And then 0 to b, yeah, x e to the x, or e over x over e to the x squared dx. And then here, if you think about it, how do you actually integrate this thing? This is kind of the hard part of this problem. Again, the integral is always the hard part, I feel. Think about it like this. Instead of 1 over e to the x squared, it's e to the negative x squared. And then you can basically do the u substitution. I won't work it all the way. Well, actually, maybe I will work it all the way out. U is equal to the inner function, which is inside the exponent, e to the x squared, du dx is equal to negative 2x. So dx is equal to du x. So if we substitute that in, think about what happens here. We get basically e to the u times x over negative 2x, right? And then the x's cancel out. So long story short, we're getting negative 1/2 e to the u, which is integrable. So we can do that no problem. Now here, what you have to pay attention to when you if you happen to be doing a u sub inside of a type 1 improper integral, you need to be sure to change your bounds, right? Like these are the old bounds in terms of x. In terms of u, we need to change them. So 0, that actually stays the same, right? Negative x squared. If you plug in x equals 0, you still get u equals 0. But this one, you got to watch it. For this value, it would be a is equal to, not in this case, well, I'll just say this. I'll say negative, yeah, I'll just say negative a squared, if you want to think of it like that. So hopefully that makes sense. Again, it's not really going to change the output, but you'll see how it goes. And then here, the good news is that this, like for the other side, it'll be the same integrand. And then we're going to take the limit, or sorry, that won't be dx, that'll be du, I mean. And then here, the limit as b goes to infinity still. But now, again, the bounds are going to change 0. Like plug in 0 to this equation, you get 0. Plug in b to the equation, you get negative b squared, right? So there, we've just done the u substitution. We haven't integrated yet. So now we can integrate. But again, what's the integral of e to the u? E to the u. So it's like if I pull a negative, I can pull a negative 1/2 out of both of these expressions. And then I get e to the u, negative a squared, 0, plus e to the u, 0, negative b squared, right? And then you kind of have to solve them independently. So if we do that, again, we still have like two separate limits here. I should write these to be clear. Limit as b goes to infinity still of that thing, and then limit as a goes to negative infinity for that limit. What would happen here? We would get e to the negative b squared minus e to the 0, and then the limit as b goes to infinity of that, right? And then basically the same thing over here. So limit, I'll just say limit as a goes to negative infinity of basically the same thing. E to the, well, it'll be e to the 0, e to the 0 minus e to the negative a squared plus that. And then we'll still have that negative 1/2. I just factored it out of both of them to make it a little easier on the outside. And now, when you get to a situation like this, you have a couple options. Basically, option one is that one of them converges and one of them diverges, right? So what's this going to be? This is going to be 1 minus e to the negative a squared. as a approaches negative infinity, what's negative infinity squared? Positive infinity, basically. But then we multiply by a negative again. So it's still going to be negative infinity. E to the negative infinity converges, if you remember your limits at infinity, because it's really like, you can also think about it as 1 over x as x goes to infinity. Well, obviously the denominator is going to blow up forever. So it's going to shrink to the whole number, right? 1 over a gigantic number is going to be 0. So that one's just 1, right? And then over here, think about it. We have plus, and then it's going to be essentially the same thing over here. There's going to be e to the negative infinity, which is also going to go to 0, minus 1. So this one's going to be negative 1. Now, in this particular case, they both happen to be finite numbers, and they actually both happen to cancel out, right? Here they cancel out. If one's a finite number and the other is a finite number, then you can just do the math, basically. And then here, if we do that, that's how we get 0, which is what we're seeing on the Desmos. The problem is, what if one is infinity? Like, what if this one's infinity, for example? Then the answers just diverge. You can't do math with infinity. Like, if one diverges, the whole thing diverges. They both would need to converge in order to do math. Or if they both go to infinity, like if you have infinity and negative infinity, you might think that's 0. That's not true. It's like, it's just the answer diverges if that happens. So hopefully that makes sense. But basically, if you get an infinity anywhere, even if you think they should cancel out, they don't cancel out. But if you get finite numbers everywhere, then you can just add them and do the math, and then the answer converges. So hopefully that makes sense. This is the most complex I can think of. Like, basically when you have to split it, when you have the upper and lower bound going to infinity. But if we check that out, I mean, looking at this, I mean, the answer certainly looks like 0 here. I'm just going to type in infinity, and then I'm going to type in infinity here. And then here, I think what's happening is Desmos is like, we're basically breaking the calculator. This is like an extremely small number. I think Desmos is actually approximating and saying that 0, or actually maybe it's just taking a second to update. There you go. Never mind. So now it's saying exactly 0. So yeah, so that's right. So that's how you think about it. That's how you would evaluate this improper integral. Those are type 1 improper integrals. Hopefully all that makes sense. If you have any questions, as usual, feel free to just drop them in the Skool community, and then I'll respond to them as soon as I see them. But yeah, otherwise, good luck on everything, and hope that was helpful. Catch you guys tomorrow.